6.4 example 2, we're going to look at another optimization problem for creating a model. So creating a model for a maximization problem with positive real number variables. A refinery produces oil and gas. At least 2 liters of gas is produced for each liter of heating oil. The refinery can produce up to 9 million liters of heating oil and 6 million liters of gasoline each day. Gasoline is projected to sell for $1.10 per liter. Heating oil is projected to sell for $1.75 per liter. The company needs to determine the daily combination of gas and heating oil that must be produced to maximize revenue. Create a model to represent the situation. This is clearly a problem that a lot of businesses and things like that are going to have. They want to maximize revenue. So let's go ahead and do this. Step 1, of course, determine our variables. So we got heating oil and we've got gasoline, so we can say that H is our heating oil. That G is for gasoline. Step 1, done. Step 2, restrictions on those variables. We're talking about heating oil, so we can have any fractions of a liter, so they can be real numbers. However, we can't have negative numbers. So the heating oil is going to be greater than or equal to 0, but it's going to be an element of the real number system. And the gasoline, same thing. It's going to be greater than or equal to 0, but it can also be an element of the real number system. You can have any fractions of liters, just not negative numbers. Step 3, we call it the constraints. That's where we're coming up with our linear inequalities. So the ratio of gasoline produced to oil produced. It says right at the beginning that they want at least 2 liters of gas for each liter of oil. So the gas is going to be greater than or equal to 2H. Okay? If we double the smaller value, the bigger one is still going to be greater than or possibly equal to the smaller value. The next one, the amount of gas that can produce. Gas, it says no more than 6 million or up to 6 million liters of gas each day. So we can say that gas is going to be less than or equal to 6 million. And for the heating oil up to 9 million liters of heating oil per day. So H is going to be less than or equal to 9 million. So we've got step 1, step 2, step 3. Step number 4 is, of course, we have to come up with our objective function. So when it says they want to maximize revenue. In the last question, we talked about minimum and maximum number of vehicles. So we're trying to, the objective function started with V for vehicles. This one we're trying to maximize revenue. So what we can start with is R for revenue. Revenue is a fancy word for how much money they make. Now, how much money they make, of course, it depends on what they sell, how much they sell. But we can roughly say that it's going to be 1.1 for gas, or 1.10 for gas, because it's $1.10 per liter, plus 1.75 for heating oil. So that's how much revenue, that's how much profit they're going to make. $1.10 per liter of gas, plus $1.75 per liter of heating oil. Step 5, we're going to graph. So for the first inequality, G is greater than or equal to 2H. What we can do with that one is we'll go ahead and say that instead of trying to find the X and the Y intercepts for that one, what we can do is go ahead and we'll call it G equals 2H. Now, I've already got G labeled as my Y-axis, so if we wanted to call it, we could say it's like Y equals 2X. In this case, we can see that the slope is 2 and the y-intercept is 0. We're going to do that. These are elements of the real number system. There were no real restrictions on the variables other than they had to be greater than 0. For this first one, equality is possible. So we can graph this using a solid green line. We're going to start at a y-intercept of 0 and graph using a slope of 2. So that means we're going to go up 2 and over 1. So if I go up to 2, I got to go over to 1 approximately right here. It's easier if I were to go up 4 and over 2, go up to 8 and over to 4. And this is going to be the line or the boundary. Kind of swerved at the end there, but that's okay. It's not going to affect it too badly. The next one we can graph is G is less than or equal to 6 million. I've got it labeled as 246,810. These are going to be our millions of liters. So I can just go ahead and call it G equals 6. And while I'm at it, I'll call the other one H equals 9. We're doing our boundaries, so we call them equals. So for G equals 6, H equals 9. Again, we've got real numbers, equality is a possibility, so it's nice. It's just everything is going to be solid green lines. So G equals 6, horizontal line through G equals 6, right here. H equals 9, same deal. Vertical line through H equals 9, about right here. Let's come up there as well. Shading is going to be pretty important here, though. So we'll just take a look at the first one. We'll go right here for H is less than or equal to 9. So since it's got to be less than or equal to 9, we're going to shade left of that one. For this one right here, where it was G has got to be less than or equal to 6. So again, it's less than or equal to, so we're going to shade below. So far this whole rectangular region that I'm sort of outlining right now, this whole rectangular region right in here has been shaded twice. And now it's up to determine the third region of shading. It's up to determine where we're going to shade in terms of that oblique line. So let's do that now. So we'll take that oblique line. It's G equals, G is greater than or equal to 2H. We can't do 0, 0 because that's on the line, but we can do something like 2, 0 right here. So 2 for H and 0 for G. So 0 should be greater than or equal to 2 times 2. 0 greater than or equal to 4. Nope, false statement. So because that's a false statement, it means this point, 2, 0, is not in the solution region, so we must have to shade on the other side of the line. So like I said before, the whole rectangle was shaded twice, but now because this point 2, 0 is not in the solution region, it must be this point above that's shaded. So this region in here has been shaded 3 times. There is our solution region. It's a beautiful thing. If you want to see it in action, you can go to page 328 of your textbooks. We can take a look now at your turn, which says, suppose that the refinery produced at least 2 liters of heating oil for each liter of gasoline. How would Umberto's model change? Let's take a look.
I used the same variables that Umberto used. The restrictions also remain the same. I wrote 2 inequalities that Umberto used in his model. G is less than or equal to 6 million, and H is less than or equal to 9 million. These inequalities do not change because they are not affected by the relationship between the production of gasoline and the production of heating oil. I wrote an inequality to show that the refinery produces at least 2 liters of heating oil for every liter of gasoline. I sketched a graph to represent the new model. The solution region is the area below G equals 0.5H and to the left of H equals 9. Both lines are included in the solution region. Since H cannot be greater than 9, G cannot be greater than 4.5. Therefore, the solution region does not touch the line G equals 6. The new model would have a solution region below G equals 6 and to the left of H equals 9, like Umberto's model did. However, the new solution region would be under the line G equals 0.5H instead of over the line G equals 2H. It would be bounded by the line H equals 9, not by the line G equals 6.
And that's it for that. Again, you guys, please come back to class tomorrow with lots of questions. We can go through whatever you need before you start working on your assignment.